Welcome back to Networking Fundamentals by Yamaha Commercial Audio Systems. I'm Pat Kalani. In this video segment, we're going to talk about the three primary settings of any network device: IP address, subnet mask, and gateway. I think most people today have a decent understanding of an IP address. It's similar to a phone number, right? If you want to call someone, you need their phone number. If you want to contact a device on the network, you need their IP address. So in this example, we have two devices on the network. We have a laptop and a mixer. Each device has a unique IP address, and a connection can be made from one to the other across the network. So in this diagram, you'll notice that there's an arrowhead indicating the connection was made from the laptop to the mixer. Just like a local phone call, both devices in the conversation know who placed the call and who received the call, and this will become important later. But for now, just know that when the connection is made, it is bidirectional. That means both parties can talk and both parties can listen. Now this may seem like a minor quibble, but you may have noticed I did not put an arrowhead from the laptop to the network switch. In most communication you'll have on your home or on your audio network, the network switch is not a destination. As a matter of fact, your network switch tries to be as transparent as possible. So you can think of it this way: you don't talk to your network switch, you talk through your network switch. Now, this difference becomes important once we start thinking about the gateway and the router. If communicating with a device on my local area network is like placing a local phone call, where I just pick up the phone and I dial the number and I can create the connection all by myself, then connecting to a server out on the internet is really more like dialing 0 for the operator, and the router picks up. Operator assistance, how may I complete your call? Your laptop gives the request to the router, and the router goes out and completes the connection out on the internet for you. So the router is a little bit different than a network switch because it bridges two independent networks. You have your local area network and you have your wide area network, in this case, the internet. Anytime a device on the local area network wants to connect to the internet, it just dials 0 for the operator, the router picks up, operator assistance, how may I complete your call? The router takes this request, picks up a completely separate phone line out on the wide area network, and makes the connection for you. Anything it hears from this handset, it repeats into this one. And anything it hears from this handset, it repeats out to the network, and so on. So this is kind of a place where the operator analogy breaks down. Typically when we called operator assistance, the operator would complete our call, connect our phone lines, and be off the connection. The router is always in the middle, creating this link across networks, right? Now that becomes important when we start talking about router throughput and things like that. There's also another difference. When we called the operator, we knew the operator's phone number. 0. 0 was the operator's phone number. So when we're dealing with IP communications, we need to know the IP address of the router. How do we know the IP address of the router? Well, when you set up a network device, you give it an IP address, a subnet mask, and the gateway. The gateway is the IP address of the router. If you look in this diagram, you'll notice that the router has two IP addresses, one on the local area network and one on the wide area network. So 192.168.0.1 is the address on the local area network. That is the gateway. Okay, so far I know I can contact devices on my local area network directly, and anything that's not on my local area network, I need to go to the gateway. Got it, okay. So how does my network device know whether to find a device on my local area network or to go through the gateway? The answer is that it uses a combination of its own IP address and its subnet mask. So first of all, a subnet mask is not an IP address. I know it looks like one, it's formatted like one, but it's not. The subnet mask is a series of flags that indicates what parts of your own IP address will form your local area network range. Let's unpack that a little bit. Here I have an example of a subnet mask 255.255.255.0. Okay, this is a very common subnet mask for a residential network. A flag of 255 means that any device on my local area network will match my IP address in this field. So, In this example, the first three fields have 255 in it. So that means any network device on my local area network will have to start with 192.168.10. Now a flag of 0 means we're going to ignore this field when evaluating our local area network range. So this field could have any number in it, and it will be considered to be on our local area network. So that's how we get to a local area network range of 192.168.10.anything. Any IP address that matches that range will be sought on the local area network. Any IP address outside of that range, and we go to the gateway. Now, this is an important concept, so let's take a couple examples and see if you can figure out whether these IP addresses would be sought on the local area network or if we would go to the gateway. So our first example is 192.168.10.18. This matches our local area network range, right? It matches our IP address in the first three fields, 192.168.10. So we're going to look for it on the local area network. How about our next example? 18.231.109.77. Now this one does not match our local area network range at all. So clearly we're going to the gateway to resolve this one. But how about our last example? 192.168.1.113. Usually when I ask this question, half the people say local area network, half the people say wide area network. Few people are confident in their answer, right? That's why we bring this one up. And the answer is that we're going to go to the gateway. And the reason is because we've only matched our local area network range in the first two fields. That third field, we have a 1, but the local area network range demands a 10. So our device will go to the gateway to try to resolve this. So if you got this wrong, don't feel bad, okay? I bring this up to demonstrate just how particular network devices can be. So long as you understand the concept, we're going to be fine. Now, what I'd like to do next is drive these points home a little more. We'll take some IP addresses, some subnet masks, rotate the numbers a bit, and we'll show you what impact that will have on your local area network range. So here are two network setups using the same subnet mask but different IP addresses. From that, they independently determined their own LAN range. Now in this example, the two devices would be able to talk to each other on the local area network because their LAN range matches. Here's another example. Again, they have the same subnet mask, but now they have different IP addresses that will yield different local area network ranges. So if we took these two devices and plugged them into a network switch together, they probably wouldn't be able to talk to each other. One device would get the IP address of the other and say, hey, this IP address is not in my local area network range, and it would go off and contact the gateway. Your typical home residential router would then look out on the wide area network to try to resolve that. Now it's looking in the wrong spot. So, changing your IP address might change your local area network range. So now let's turn the tables a little bit. Let's keep our IP address the same, but change our subnet mask and see what effect that has. In our first example, you can see that we have a subnet mask typical of a residential network, 255.255.255.0. So in this first example, we have one field where we can change our IP address and still be within the local area network range. The values can go from 0 to 255. There are some reserved numbers in there. We'll talk about that later. But for now, let's just say that that's over 250 addresses. Now, the next example, we have a subnet mask of 255.255.0.0. So in this example, we can vary our IP address in two fields and still be within our local area network range. Each field could have a value from 0 to 255, again, some reserved ones, but let's say that gives us over 65,000 addresses available to us. 250, 65,000. So changing our subnet mask changes the size of our local area network. Hopefully that's clear. Now so far, we've just talked about subnet masks using flags of 255 and 0. And that'll cover most of your residential or your Dante audio networks. However, If you're working with an internet service provider, they might give you a tighter range. Or if you're working with a larger property network and you're doing something a little more complex, you might be opening it up a little more. So in both of these examples, you're probably just going to type in the numbers given to you by an IT professional. However, I think it's helpful to understand what these numbers do and how they work. It'll further your understanding of what we've covered so far. It will make you more conversant with an IT professional, and it will prevent embarrassing typographical errors when you're entering these numbers. So, what we'll do is we're going to crack the hood a bit, and we're going to show you how the subnet mask works at a lower level. In the examples, I've already done all the decimal to binary conversions, so we're going to be focused on concept. We're not going to get bogged down by arithmetic. So hold on, here we go. So the first thing to realize is that an IP address is really a 32-bit number. Each field of the IP address can be a number from 0 to 255. For some of you, that might ring a bell as an 8-bit range. So 4 fields, 8 bits each, 32 bits in total. So far, we've been dealing with subnet masks made up entirely of 255 and 0. Now in this example, you can see that 255 in binary is 8 bits worth of ones. And a 0, of course, is all zeros. So don't think of the subnet mask as a series of 4 flags. It's a series of 32 binary flags. So each binary 1 in the subnet mask means our LAN range must match our IP address in this bit position. So that evaluation is done 32 times across. The reason why 255 and 0 are so easy to work with is because they evaluate an entire field at a time. So it really allows us to keep things at the decimal level. So this brings us to a simple point. You might see an IT professional abbreviate this IP address and subnet mask as 192.168.1.0/24. The /24 indicates there are 24 binary ones in the subnet mask. Now that brings up an interesting question. Could it be another number? Sure. If you look at this subnet mask, we have 255, 255, 252, 0. And if you look at the binary line, there's a total of 22 binary ones in the subnet mask. So the reason why this one gets tricky is that 252 in the third field. You'll notice in binary, the first 6 bits have ones in it. So that means the first 6 bits of our LAN range have to match our own IP address. And the last 2 bits have zeros. So those are free to be ones or zeros however they want. So here I've got this all worked out for us. If you look at the binary line, you'll see the first 6 bits are in red. When we're determining our LAN range, these have to match our IP address. Now the last 2 bits I have in green because those are the ones that can vary, right? So I've put the highest and the lowest values in there. So as we look at this, the binary value of our LAN range can go from 0 to 11. When we convert that to decimal, that's 0 to 3. Now I made this one fairly simple by picking an IP address that would give us zeros in those first 6 bits. As we look at our decimal range, you can see that gave us a value of 0 to 3 in our LAN range. Now that's a total of 4 values. Don't forget to count 0. So you have 0, 1, 2, 3. 4 values. Okay. Let's take a look at what would happen if we change our IP address. So in this example, we still have the same subnet mask. So I know that third field of our LAN range will still yield 4 values. However, because our IP address is a higher number, it's got some binary ones in those first 6 bits. So now if you look at the binary line, you're going to see a combination of ones and zeros being copied from your IP address into the LAN range. So when you put it all together, you have a range of 11000 to 11011. So once you do your decimal conversion, that gives us a range of 24 to 27. Again, that's still 4 values, right? 24, 25, 26, and 27. All of those numbers would be counted as our local area network range. So let's get back to this network shorthand notation. I added this to our lesson plan for 2 reasons. Obviously, if an IT professional emails you something in this notation, you'll know what they're saying. But secondly, this shorthand notation really embodies the generally accepted best practices for subnet masks. Most IT professionals will agree that we want our subnet masks to go from a chain of binary ones to binary zeros. So the subnet masks we've been working with so far fit that splendidly, right? 255, 255, 255, 0. It's 24 ones followed by 8 zeros. No problem. So here's an example of a subnet mask that does not fit our best practices. 255, 0, 255, 0 will go from a series of binary ones to binary zeros back to binary ones. That's a party foul. Basically what happens is you end up creating a checkerboard of values that are in the LAN range, then out of the LAN range, then back in the LAN range, and it really makes it difficult to manage. So here's another example of a subnet mask that does not fit our best practices. 255, 255, 15, 0. Now that third field with the 15 in it, that violates our best practices all by itself. It transitions from binary zeros to binary ones within the same field. So if you think about it, you might start to realize there's a limited number of flags that we can use in our subnet mask and still fit our best practices. And here they are. So we already know 255 is a chain of all binary ones, and 0 is a chain of all binary zeros. All of the other flags in the middle will represent the change from binary ones to binary zeros mid-field. So in following our best practices, you could have multiple 255s in your subnet mask. You could have multiple zeros in your subnet mask. But any of the numbers in between could only appear once because they will represent that transition from binary ones to binary zeros. Okay, now we've covered a lot of ground in this video. So let's take a couple of review questions and make sure the key points are sticking. Question number 1, what is the gateway? Well, the gateway is the IP address of the router. Remember, when you want to contact a device on your local area network, you make that connection directly. But if you want to contact a device that is not on your local area network, you need to contact the gateway, the router, which will then help you make the connection to the outside world. What are the easy subnet mask flags? Well, the easy flags are 255 and 0. When you're determining your LAN range, a flag of 255 means that any device on my local area network will match my IP address in this field. And a flag of 0 means you could put any number in that field and we'll consider it to be on our local area network. No problem. Do the following subnet masks fit our guidelines? Let's try this one, 255.192.255.0. No, this one doesn't. Remember, our best practices want a subnet mask that is going to transition from binary ones to binary zeros. This subnet mask fails that test. The 255 in the first field is fine. The 192 in the second field is even okay. That's one of our acceptable flags. But that creates a transition from binary ones to binary zeros. The 255 in the third field means we're transitioning back to binary ones, so we fail the test. How about 255.255.128.0? Yes, this one fits our guidelines. 128 is one of the acceptable flags that transitions from binary ones to binary zeros. Before it, you've got all 255s, and after it, you've got a 0. So this one fits perfectly. How about 255.255.103.0? No. 103 is not one of our accepted flags. Right within that field, it will create a transition from binary zeros back to binary ones. So that's a problem. How about 255.255.255.254? Yes, this one does meet our guidelines. The 254 in the last field is one of the acceptable flags. We only have one transition from binary ones to binary zeros. Now, if you work this one out, it's a very small local area network range. It only yields 2 addresses, but it meets our best practices. So how about 255.255.248.0? Yes, this one does meet our guidelines. 248 is one of our acceptable flags. We only have one transition from binary ones to binary zeros, so we're good. So here's a question I get every now and then. Why wouldn't I use a subnet mask of 0.0.0.0? It kind of fits our best practices, right? Because we never transition from binary zeros to binary ones in that subnet mask. But to me, the real answer is that you never have an opportunity to go to the gateway. Every IP address you throw at that subnet mask would be determined to be on your local area network. You would never go to a wide area network, and you would never go to the internet. Well, that wraps up this video segment. I'd say we have thoroughly covered the three core settings of any network device: IP address, subnet mask, and gateway. With even a moderate understanding of the topics we've covered in this video, I think you'll find subsequent videos much easier to understand. Thank you for joining us, and I welcome you to check out our next chapter, where we'll discuss reserved LAN ranges and reserved IP addresses.